Hello, in this video, we are going to take a look at another example of using trig substitution to evaluate an integral. So in this integral, we have the square root of 4x squared minus 1 all over x. In general, we can see we have the form of x squared minus a squared. And in that form, we know we want to make the substitution x equals secant a secant theta. However, we don't have x just by itself. We have a 4 with the x. That isn't terribly hard to rewrite. We can rewrite this 4x squared as a square root of 4, or 2x, all of that squared. We now generally have something in this very similar form. And instead of just making x equals a secant theta, we will make the full substitution of 2x equals a secant theta. And in this case, a is 1, because 1 squared is 1. So we're making the substitution of 2x equals secant theta. With a little bit of a rewrite, we also have x equals 1/2 secant theta. We could have also divided everything in that numerator by 4 and divided everything in the denominator by 4 to get a similar rewrite. Now, because x equals 1/2 secant theta, dx equals 1/2 secant theta tangent theta d theta, we are ready to make our substitution. So substituting all the x's out for the substitution, we get the square root of secant squared theta, because 2x is secant theta, minus 1 all over 1/2 secant theta times 1/2 secant theta tangent theta d theta. Secant squared theta minus 1 is tangent squared theta. 1/2 secant theta here and 1/2 secant theta there cancel. So we have the integral that the square root of tangent squared theta, or tangent theta, times tangent theta d theta, which is also the integral of tangent squared theta d theta. We have simplified down to a trig integral. After we get down to a trig integral, we want to evaluate it. We have tangent squared. We know really well what to do with an odd tangent. We know really well what to do with an even secant. Tangent squared, we need to think about a little bit more, but we've actually already used what we're going to want to use. Earlier in this problem, we used that secant squared theta minus 1 equals tangent squared theta. We can use that again to turn this integral into the integral of secant squared theta minus 1 d theta. And I do know how to integrate secant squared. I do know how to integrate 1, making this the integral of secant squared theta is tangent theta, and the integral of 1 is theta plus c. The last thing we need to do is get these thetas back in terms of x using our substitution. So off on the side, I'm going to rewrite the substitution we had. We had 2x equals secant theta, or 2x over 1 equals secant theta. This also means that theta equals secant inverse of 2x over 1. And secant is the reciprocal of cosine. So it's much easier to work with sine inverse, cosine inverse, or tangent inverse. So going to rewrite the secant inverse as a cosine inverse, that will take the reciprocal on the inside. So cosine inverse equals 1, cosine inverse of 1 over 2x equals theta. Setting up our triangle, cosine equals adjacent over hypotenuse, which is 1 over 2x. So we're going to put a 1 on our adjacent side, a 2x on our hypotenuse, and get a 2x squared minus 1, all of that square rooted, as our opposite side. What this tells us with the triangle is that tangent theta, which is opposite over adjacent, is the square root of 4x squared minus 1 all over 1. With this piece and this piece, we can put our integral back in terms of x to have the square root of 4x squared minus 1 all over 1, which doesn't need to be written, minus theta is cosine inverse of 1 over 2x plus c. And there is our integral of the square root of 4x squared minus 1 all over x.